Today we're going to look at inhomogeneous difference equations, and as always I'm going to show where it comes from, some motivating examples, and then towards the end I'm going to give kind of the method that you should follow. So the reason this is inhomogeneous is because we have terms in the sequence, tn's and tn plus 1s, but we also have other terms. We have a 1 here, which is just a constant, and we have a 2n, which isn't a term in the sequence, it just depends on what n is. And the first step to solving this is to solve the corresponding homogeneous equation. So before I do that, actually, usually when we're solving these, we bring all the tn stuff to one side and leave everything else on the other side. So I'm just going to rewrite this as tn plus 1 minus 3tn is equal to 2n plus 1. So what I'm going to do now is the first thing we have to do is we solve the corresponding homogeneous equation, and this will give you a bit of an insight into how we solve these and why we solve it. So the corresponding homogeneous equation will be tn plus 1 minus 3tn equals 0. So as an exercise, warm-up exercise, I would suggest that you solve this, because you should be able to solve this. You don't need to figure out what the constants are. You don't have to use this, because it's going to change, but you can if you'd like. So yeah, solve this as a little warm-up. And I'll solve it as well, just to kind of bounce off the last video to show how we can use the second order method for first order ones. So we need to figure out what the roots are for our exponential. So what we do, remember, is we start at the lowest ordered term, which is a tn, and that's going to be a constant. So that's just minus 3. Then we go to the next term up, and that's going to be an r. And then if we had a tn plus 2, then we'd have an r squared, and then we'd solve the quadratic, we'd have 2 roots. But because it's first order, we only have 1 root. So we get that r equals 3. And then what we do is our solution then will take the form some number multiplied by 3 to the power of n. Okay, and we can check that, and let's check it real quick. So if this is true, we should be able to sub it in here, and it will be correct. So that would mean we need to figure out, sub into here, we need to figure out what tn plus 1 is. So tn plus 1 would be a times 3 to the power of n plus 1. So now let's sub in. So then we get a times 3 to the power of n plus 1, that's tn plus 1, minus 3 times tn, which is a times 3 to the power of n. A times 3 to the power of n. So again, I'm just replacing this part with this, and I'm replacing this part here with this, okay? And we can see that this is clearly true, because when we multiply this 3 in, we're going to get 3 times 3 to the power of n plus 1 here, and then these are the exact same, they'll cancel each other out, it's equal to 0. Cool. So that's how we know that that's the solution, and here we are. Okay, so how do we go about solving the inhomogeneous version? So I'm going to get rid of this. We're just going to talk about this. This is just rearranged. I just brought the tn term to the other side. So first of all, we know this is our solution right now. We know with this solution, this part's going to be equal to 0, but we don't want this to be equal to 0. We want this to be equal to 2n plus 1. So one thing that you might guess to do is, well, let's just add on 2n plus 1. And let's see what happens. So if this is tn, well then what's t of n plus 1 going to be? Well, we have to add on the 2 times n plus 1 plus 1. So if this is our solution for tn, well then our solution for tn plus 1, we have to replace this n with an n plus 1, and same with the story with this n. So I'll just simplify a bit. This will be a times 3 to the n plus 1 plus 2n plus 3. And that's just combining terms here. And let's check if this is a solution. I don't think it will be, but let's check. So tn plus 1 up here, I'll start color coding again. Tn plus 1 here, that's going to be this. Sorry, it's not going to be that, it's going to be this. So we'll have a times 3 to the n plus 1 plus 2n plus 3. Then we have minus 3tn. And what's tn? Well, tn, we're guessing, is equal to this. And we'll get a times 3 to the power of n plus 2n plus 1. And that should be equal to 2n plus 1 from this equation. And if this is true, we found the solution, but it's not going to be. So same as last time, as we expected, this is going to cancel out with this, and that should make sense, because remember that when our solution for the homogeneous equation was equal to 0, so this part is the homogeneous part, and they cancel each other out, they're equal to 0. That should make sense. However, we have 2n here, then we have minus 6n, that'll be minus 4n. So we're kind of on the right track, except we have minus 4n, but we want 2n on both sides. And in terms of the constants, we have a 3 here, and then we have minus 3 times 1. So we end up getting a 0 on the left-hand side, but on the right-hand side, we actually want a 1 on both sides to make sure both sides are equal. So that's not quite the solution. But you can see that we have something linear on the left-hand side, so that's good. We just clearly have the wrong coefficients, because when we add all these things together, we don't get 2n on the left-hand side, even though we should have it, because it's on the right-hand side. And on the left-hand side, we should get 1, so it matches the right-hand side, but we don't. But it's going to be some kind of linear. So basically, we know that our solution, in reality, is going to be some kind of linear. So instead of being 2n plus 1, let's just call it alpha n plus beta, if something like that, whatever you'd like. So I'm going to get rid of this because we know it's wrong, but instead we're going to call it alpha n plus 1 plus beta. And the reason this one's an n plus 1 is just because this is t of n plus 1. So now we can figure out what alpha and beta, we can sub in again, and instead of just guessing and subbing in, we can actually figure out what alpha and beta are. So we don't have to sub the whole thing in though, so we don't have to sub in this part, and the reason we don't have to sub in this part is because we already know this will cancel out with this. We already know that. I showed that to you a few seconds ago. So we only have to actually worry about subbing in this part to our original equation, figure out what alpha and beta are. Because we already know that the homogeneous part, I'm going to keep calling this the homogeneous part, we know that that's equal to 0. Okay, cool. So that means we only have to sub in this part, the alpha n plus beta. So t of n plus 1, I'll start color coding again. Tn plus 1, we're going to be subbing in this. So I'm going to say that's alpha n plus alpha plus beta. So that's just multiplying out this bracket. So that's being subbed in here. And then we're going to have minus 3, and then we're going to have tn. So tn, what are we going to sub in? I'm just going to sub in this part. Again, because we already know that these bits will cancel out. So we don't need to sub those in. We already know that's equal to 0. So then what we can do is sub in, we'll have alpha n plus beta. And we want that left-hand side, some kind of linear, we want that to be equal to 2n plus 1. And now we can actually figure out, because this is an identity, as in both sides should always be equal, we can figure out what alpha and beta are. So basically what we find is, I'll multiply this out, we'll have alpha n plus alpha plus beta minus 3 alpha n minus 3 beta, sorry. That'll be equal to 2n plus 1. Now we can group all the n's together on the left-hand side. So we have alpha n minus 3 alpha n, so we'll get minus 2 alpha n. And then we have all the constants, which is alpha plus beta minus, well, beta minus 3 beta is minus 2 beta. So we'll have alpha minus 2 beta. Okay. And that should be equal to 2n plus 1. And this should always be true if we want a solution. So that means that minus 2 alpha should be equal to 2. Minus 2 alpha should be equal to 2. This tells us that alpha is equal to minus 1. And we also know that alpha minus 2 beta should be equal to 1. So again, this part should be equal to this part. And this part should be equal to this part. We know that alpha is minus 1. So that means that minus 1 minus 2 beta is equal to 1. Bring the 1 to the other side. Then we get minus 2 beta equals 2. And this tells us that beta is also equal to minus 1. So we've just figured out what alpha and beta should be. So what it should be, our solution, Tn, we know what alpha and beta are now. So it should be minus n minus 1. Okay. And you might want to check this. Well, how we just figured out that this is a solution, but you might want to sub this back in to the original equation and see if it's a solution. So I'll do that very quickly. So if this is Tn, well then Tn plus 1 should be equal to a times 3 to the n plus 1 minus, so instead of n, we're going to have n plus 1 minus 1. So that'll simplify to be a times 3 to the power of n plus 1. We'll have minus n, and we'll have minus 2. Okay? Because this minus 1, minus 1. So I'm not going to sub this part in, because we already know that this part will cancel out with this part. I'm only going to sub in these two parts, and I'm going to show you that they cancel out. Okay? So we'll have minus n minus 2, minus 3 times minus n minus 1. Is that true that that's going to be equal to 2n plus 1? So again, I've just subbed in for tn plus 1 and tn on this side, and we want to see if that's equal to 2n plus 1. Well, what do we get? We have minus n minus 2, then we'll have plus 3n plus 3. And as you can see, that's going to be 2n plus 1. So yeah, we just found a solution. That's pretty cool. Great. Okay, cool. So we found a solution. Now we need to figure out, of course, what a is. And we just do that the same way as we did before. So the way we always do that is we know that t0 is equal to 3. So we come down here, we say that t0 is equal to 3, which means, so that's going to be equal to a times 3 to the power of 0 is just 1. Minus n is 0, so 0 minus 1. So that means that we're going to have 3 is equal to a minus 1. That tells us that a is equal to 4. Cool. And now we have found our exact solution. So now Tn will be equal to 4 times 3 to the power of n minus 1. And you can sub this in and it will be true always. Now you might think, oh, could I have solved for a before we did this part? And the answer is no. You have to solve for a at the very end, because if you solve for a before you do the an plus beta part or the alpha n plus beta part, you're going to get a different answer for a here. and then when you add in this part, it's not going to line up anymore. So basically, when we're adding in this part, it's going to change the value of Tn. So if we originally solved it to make sure that T0 is going to be equal to 3, as it says up here, well then now, once we add on our alpha n plus beta, we're going to end up changing that number. So I'd encourage you to mess around with that yourself, but I think it should make sense, because if you solve for a here, you're going to get some number to make, and this it guarantees that T0 will be equal to 3, which is what we want, but then if you're adding extra stuff on, that's going to change it. So it's no longer true that T0 is equal to 3. So that's why you have to do that at the very end. So that's the general gist behind why it works, and now I'm going to give you kind of a full method to follow. So I'm just going to use second order to keep this very general, but it could be first order as well, if a is equal to 0. So basically, we have some kind of difference equation, and I brought all of the, sorry, I've written this wrong. So we have this difference equation, and we have all the homogeneous part on one side, and then we have the other part on the other side. I've just called it f of n, which is some function of n. So basically, in our case here, f of n was a linear function, but f of n could be any kind of function. For the Leaving Cert Maths course, or Applied Maths course, sorry, it'll be either a linear, a quadratic, a constant, or some kind of exponential. That's kind of the only things they'll ever ask. So the idea is, basically, the first thing we do is we solve the homogeneous equation. The homogeneous. So basically, we solve this thing equals to 0. And why are we doing that? Because if we solve this thing to equal to 0, well then we know that this part will all be equal to 0. So then we get some solution. So our solution for Tn will be a times our first root to the power of n plus b times our second root to the power of n. Of course, if we have repeated roots, it's a bit different. This is just the case where they're different roots. Remember, with repeated roots, we multiply the second term by an n. And we know that this part of the solution will make this part equal to 0. Okay, cool. So that takes care of that part. Now we have to take care of the f of n part. So we need to add something onto this to take care of the f of n part. Because right now, our solution will make this equal to 0, but we want this to be equal to f of n. So let's, basically what we have to do is we have to add on a generalized version of f of n. And I'll tell you why now. So let's say f of n is a linear function. Let's say f of n was like 3n minus 7. Well then, remember what we guessed when we guessed up here that it was the exact same. We guessed that it was we just add on for our final solution. We guessed we add on 3n minus 7. But then when we subbed it in, we found that the numbers don't line up to give us 3n minus 7 on the other side. So what we have to do is we have to say, we know it's going to be some kind of linear, and we need to choose the coefficients to make sure that the coefficients are always going to be equal to 3n minus 7. So if our function of n on this side is 3n minus 7, well then on this side we want to have some kind of linear function, and then we need to figure out what the coefficients are so that this side is always equal to 3n minus 7, and then we have a solution. So instead of adding on 3n minus 7, we'd add on, I don't know, alpha n plus beta. Or you can call the letters whatever you want. Xn plus y if you want. And then what we can do is we can sub this into here, and then we can figure out what alpha and beta are. Because we know this part's equal to 0, we don't have to worry about that part. Figure out what alpha and beta are. And then once we know what alpha and beta are, we can solve for a and b, given that t0 is equal to x and t1 is equal to y. We can just figure out what a and b are. So how about other cases? I'll go over all the cases here because we have to take a different guess. So what if our function was some kind of quadratic? Well, in that case, we'd want to add on a quadratic, and we have to generalize it, remember, okay? So alpha n squared plus beta n plus, I don't know, gamma, or something like that. And it's very important that you don't just say alpha n squared, because it could be any kind of quadratic. And the reason for that is, see this tn, I'll give a quick explanation. See this tn plus 2? When we sub into that, we're going to end up getting alpha times n plus 2, the whole thing squared. And then that'll give us alpha times n squared plus 2n plus 4. So you can see, even though this part is just an n squared, on the left-hand side, we're going to have a mixture of n's and constants. And we need to make sure that these parts all cancel out. Whereas if we didn't have any beta n plus gamma, well then these parts probably wouldn't cancel out, and we wouldn't have both sides being equal. So it's important that whatever the function of n is on the right hand side, you generalize that as much as possible. So if it's a quadratic, we have to say a very general quadratic, and then figure out what alpha, beta, and gamma are. Play around with this if it doesn't make sense, and you'll see why you can't just say alpha n squared. The other kind of function we could have is a constant. So let's say if it was just 8. You know, in which case we would just add a constant. You can just call it alpha, and then you can just sub it in. So the way that that works is, if it's just a constant, that means that tn plus 1, that'll still be the same constant. Well, it'll be all the other stuff plus that same constant, and tn plus 2 will be all that other stuff. Plus, again, it's the same constant every single time. It doesn't change. The last thing they'll realistically ask is, what if f of n, for example, what if it's 3 times 2 to the power of n? Well, in that case, on the left-hand side, we want to add some number, let's call it alpha, times 2 to the power of n. And the reason for that is because on the left-hand side, when we sub in, we're going to get a bunch of 2 to the power of n terms, sorry, up here. On this side, we're going to get a bunch of 2 to the power of n terms from here, and we need that to be equal to 3 2 to the power of n's. So we need to figure out how many 2 to the power of n's do we need on the left-hand side, sub it in, figure out what alpha is, and then that, when it all cancels out, or when we simplify everything, it'll be equal to 3 times 2 to the power of n. Even if it was just 2 to the power of n on the right-hand side, on the left-hand side, if we just put in 2 to the power of n, well then this part is going to have a 4, so I can demonstrate that real quick. This part here would be 2 to the power of n plus 2. So it'll end up being 4 times 2 to the power of n for that reason. 4 times 2 to the n. This part here would be 2 times 2 to the power of n. This part here would be 2 to the power of n. And when you add all these up, you'll get 7 2 to the power of n's. But on the right-hand side, we just have 2 to the power of n. So that's why it's always going to be multiplied by something in front. And we need to figure out what that is in order to make sure that this side is all equal to 2 to the power of n. Same on this side, so that it matches this side. So that's essentially the method that we're doing. So what we do is we solve the corresponding homogeneous, and sometimes this is called the complementary solution. So you might want to solve it and then put it to the side. And then the other solution is sometimes called the particular solution. And this is like our generalized form of f of n. So for example, if it's an exponential here, we'll have some number times 2 to the power of n. Then what you do is you figure out what this alpha is for this particular solution, which is what it's sometimes called. Figure out what that alpha is, and then your final solution is you add these two bits together, as shown above, and then you can figure out what a and b are by using t0 and t1. So in the next few videos, I'll probably go through a few examples, but yeah, that's the method, and that's all shown in the summary video as well. So here are some past higher level questions you can try if you'd like, and as you can see, it comes up twice pretty much every year. The reason it's not up twice in 2025 is because it wasn't another question, it's just that it was a homogeneous one, and same on the sample paper, I believe. Yeah, it was the same on the sample paper, but it's homogeneous. So difference equations often come up across 2 questions, and inhomogeneous ones are kind of the final step. So yeah, here's some questions that you can practice with.